Okay, so welcome to the lecture of this finite volume method. So now we are talking about the governing equations. Now we will look at the equations in the general form. That means we want to write the equations in the general conservation form. So which will club everything together. Okay. So what we have looked at so far is the mass conservation, momentum conservation, energy conservation and energy in different forms. Now we will put everything together in one particular form. So what you can say, let us say the any variable, physical variable phi, that is what we have been doing it, physical variable phi. It could be now your change of phi over delta t time within the material volume mv. Okay. This is what is the left hand side of the system equals to surface flux of phi over delta t across control volume. So that is one term plus source or sink of phi over delta t within control volume. So that is essentially my term 1, that is my term 2 and this is term 3. So if you expand this term 1, so this is nothing but ddt of material volume rho phi dV. So in the integral it be del t of rho phi plus del dot rho v phi dV. Okay. And this rho v phi is the transport of phi by the flow field, or you can say the transport of the property phi due to underlying velocity field over there. Okay. So essentially this is my convection flux. So I will designate that one convection equals to rho v phi. Now I have the similarly the diffusion flux. Okay. So that is minus gamma phi delta phi, or you can say simple gamma delta phi. So my term 2 that becomes minus surface integral j phi dot ds, which is delta dot j phi diffusion flux dV, and if you write over volume it is delta dot gamma delta phi dV. Okay. And term 3 which is the source term essentially. So over the control volume you write qv dV. So this could be any source term, this could be any source term, source or sink term. So it is in the general notation. So if I put this together, then my system will become rho phi plus delta dot rho V dV equals to delta dot gamma delta phi dV plus the source term B. So, you take everything over one integral and then you can write certainly rho V phi minus delta dot gamma delta phi minus q b dV 0. So, which gives me back the system of minus q b equals to 0. Okay. So, if I write them in slightly simplified form, this plus delta dot j phi minus q phi equals to 0, and j phi is a combination of both my convection plus diffusion fluxes, which is rho v phi minus gamma del phi. So, the equation system will becomes del del T of rho phi plus delta dot rho v phi equals to dot gamma delta phi plus q phi, and in the other way around, if I put things together, so these two equations are essentially equivalent, and I can write in a generic format like del del T of rho phi plus delta dot j phi equals to source term of phi, and this j phi is the diffusion flux, convection plus diffusion flux due to diffusion. So, this will take care everything in one simple form. So, that means if you look at this particular equation, this can be used for continuity, this can be used for momentum, this can be used for energy, this can be used for species transport equation. So, you take any transport equation, they can be put together in this particular format. Okay. Now, it comes to the normalization of the Navier-Stokes equations or the non-dimensionalization of the Navier-Stokes equation. So, if you just consider a Cartesian coordinate system, Cartesian 3D coordinate system, okay, and if you consider that as a sign convention x, y, z, then you have a continuity equation, okay. Then I have a momentum equation, I mean basically x momentum equation, del u plus del y plus del del z rho w equals to minus del p del x plus mu del t u by del x2 plus del 2u by del y2 del 2u by del z2. Similarly, my y momentum equation would be del rho v plus del del x of rho u v del del y of rho v v minus del p del z plus mu del 2 v by del x2 and if you have a source term, so just this one you put x, this one y, this one z. So, the source term acted in this direction, gravity. So, you take rho g in the y momentum equation, and del T of rho w plus rho u w rho v w z plus and the temperature equations, if you write Cp del T rho T plus del x of rho u T rho v T equals to kappa delta T 2 x 2 plus. So, here the temperature equation does not have any source term, and if you look at the complete set of equations, they are in a conservative form. Now, to non-dimensionalize the system, you need the referencing velocity. So, that is you say that you reference the referencing length scale, that is L reference, then you have viscosity mu rep, density reference. So, all these reference scales you use. Now, the velocity that you need to scale by the, so one is the scaling of the velocity, and then the scaling of the, one is scaling of velocity, another is the scaling of pressure. So, once you do the scaling and then we use them in the equation system. Okay. Now, one more important thing that will come is that, so obviously you will have a time scale and all these things. Now, that since we are using the temperature equation, that delta T with the reference temperature, that you take into account. So, T infinity is your reference temperature, and the density variation if you take with respect to temperature. So, you take with the Taylor series expansion with the only retaining the first order term, and this beta is defined as the coefficient of volumetric expansion. This is coefficient of volumetric expansion. So, you take the beta is 1 by rho d rho by at constant pressure. So, rho becomes rho infinity 1 minus beta T minus T infinity. Okay. So, using that you actually substitute this one in y momentum equation. Okay. So, then your scaling parameters. So, one is the first thing will be the x, the scaled x would be x by L, y is y by L, z is z by L. Then the velocity scaling u would be u by mu by rho L. Similarly, v is v by mu by rho L. Then w is w by mu by rho L. Then your time T divided by rho L square by mu, pressure is P plus rho g y divided by mu square rho L square, and temperature T minus T infinity divided by T max minus T infinity. Okay. So, all this tilde represents the scaled or non-dimensional values. Now, if you put them back together, for example, let us say if I take the first derivative or del u by del x, which is essentially going to be del of mu u hat divided by rho L x hat. So, if you take that mu by rho L outside and L outside, this will become rho u hat by del x hat. So, essentially this is mu by rho L square del u hat by del x hat. Similarly, I can done the del T of rho u. So, del T of rho u would be del of mu u hat L divided by del of rho L square T hat by mu, mu by L divided by rho L square by mu. So, this will become del u hat by del T hat. So, essentially this is mu square divided by rho L cube del u hat by del T hat. Okay. Similarly, you can have a term with del T of rho u, because this is there in my momentum equation. So, this would be del mu square by rho L square u hat divided by del L x hat. So, it becomes mu square finally by rho L cube del u hat by del x hat. So, you can do other terms also, like for example, if you do the pressure term. So, this will become P plus rho g y divided by mu square by rho L square. So, if you transform them and then take the term of del P by del x, this will become mu square by rho L cube del P hat by del x hat. Now, diffusion term mu del 2 u by del x 2. So, that would be mu del 2 u hat by rho L hat square. So, finally, it becomes mu square divided by rho L cube del 2 u hat divided by del x square. And the final term, that is rho g beta T minus T infinity. So, that becomes rho g beta T max minus T infinity T hat. So, this would be rho g beta delta T T infinity. Okay. And one more term in the energy equation, if you look. So, you will have the term del T of rho T. So, this will become mu delta T divided by L square del T by del T hat. So, similarly, if you put and if you transform and substitute all these back, to the system of equation. So, your continuity equation becomes now only del So, there is no change with the continuity equation except the hat. So, this is my non-dimensional form of continuity equation. X momentum equation, so that becomes del del t of u hat del del x hat u hat plus del del y hat u hat v hat plus del del z hat u hat w hat equals to minus del p hat by del x hat plus del 2 u by del square plus del 2 v by square by del square. Now, my y momentum equation, that becomes del v hat by del t plus del x hat u hat v hat plus del y hat then del equals to minus del p hat plus del 2 del 2 v hat by del y2 square plus Grashof number with t hat. So, look at this particular term. So, that is a non-dimensional term or parameter which is coming there, and z momentum equation will be again similar. So, there will be no extra term. Plus the diffusion term. And the temperature equations, that becomes del t hat by del t plus del y hat p hat t hat plus equals to 1 by Prandtl number into del t hat square plus del 2 square. So, if you look at it, there is another component or the term which comes in the temperature equation. So, essentially your Grashof number is g beta delta t L cube by nu square, and Prandtl number is mu Cp by k, where nu is your mu by rho. This is kinematic viscosity, this is dynamic viscosity, this is density. So, once you do the non-dimensionalization, then you come across with different non-dimensional parameters. So, what are those non-dimensional parameters? So, one of the important non-dimensional parameter which come across is the first thing is the Reynolds number. Okay. So, Reynolds number is one parameter which is typically represented at Re, which will be rho u L by mu. So, essentially this is a ratio of two forces. One is the inertia forces to the viscous forces. So, that actually dictates if the flow is laminar or turbulent depending on the Reynolds number, and where the Reynolds number is going to be dominant. Let us say for example, if you look at a flow over a flat plate, the flow actually propagates like that, and through after some region it goes like that. So, this particular region up to some Reynolds number, this is a boundary of Reynolds number 1, then this is the Reynolds number 2. So, in this zone the flow is laminar, then this zone it is turbulent. So, depending on actually the Reynolds number, one can classify the flow to be laminar or turbulent. Now, the other parameter which is coming is the Grashof number. So, Grashof number is nothing but the ratio of the buoyant forces to the viscous forces. So, this appears due to non-dimensionalized in the equation of the temperature equation. Now, Prandtl number. Prandtl number is another non-dimensional number which is essentially the ratio between momentum diffusivity to thermal diffusivity. So, if you look at the Prandtl number, this will be mu Cp by K, essentially I can write that nu by alpha. Okay. Now, depending on the Prandtl number, so Prandtl number could be greater than 1 or Prandtl number could be less than 1. Now, depending on the Prandtl number, actually it is a ratio between, if the same flow, if you look at it and the flow evolves over a flat plate, then these are the two layers. Okay. If Prandtl number is less than 1, that means your momentum diffusivity is less than the thermal diffusivity. So, this will be your hydrodynamic layer or boundary layer, and this is your thermal boundary layer. While Prandtl number will become greater than 1, this would be completely reverse. So, then your now another non-dimensional number is called the Peclet number. So, the Peclet number typically is represented by Pe, and this is rho u L Cp by K. Essentially it is a product of Reynolds number into Prandtl number. So, it is a ratio of advective transport rate to its diffusive transport rate. So, it is a ratio between these two things, and this would be the number which will be very important while we will be actually doing the finite volume discretizations, and over a cell we will look at what is the conditions on Peclet number. Now, once you go back, then there will be another number called the Smith number. So, that is SC. This is again the ratio of the momentum diffusivity to mass diffusivity. So, this is momentum diffusivity to mass diffusivity. So, this will be another important parameter when people look at the species mass transfer equation. Now, in the heat transfer there will be an non-dimensional number which you will require is the Nusselt number. So, Nusselt number is estimated at HL by K. So, where H is your convective heat transfer coefficient. Now, one more for the case of Mach number. So, this essentially is the ratio of your sound speed to the velocity scale, and A is your sound speed at a given temperature, and you can estimate is a gamma del p by del rho at a typically this is gamma r t. So, these are the number that comes across, and this will determine whether the flow is subsonic, supersonic, sonic or supersonic. So, depending on the Mach number, you can define different regime of the flow field. Okay. So, this is another number which appear in the heat transfer problem is the Eckert number. So, that actually correlate the kinetic energy to the flow enthalpy. So, it is essentially the kinetic energy ratio of the kinetic energy to flow enthalpy. So, this is, and when you talk about the hydrodynamics, then you get Froude number, which is typically represented Fr, which is ratio between U by root GL. So, it is a characteristics velocity, scale between characteristics velocity to the gravitational wave velocity. It is a ratio between these two numbers, and when you deal with the multiphase system, then you come across Weber number, which is rho u square by L by sigma, which is the ratio between inertia forces to surface tension forces. So, these are the non-dimensional number that actually you need to know when you actually non-dimensionalize the system. So, now once you non-dimensionalize the system, under different condition you come across different number, and this is where you need. So, what we have talked so far is the all the governing equations and their non-dimensionalizations, and once you do the non-dimensionalization, though what kind of number you come across. So, we will stop here today and we will take from here in the follow up lectures. Thank you.